So we started off this chapter talking about distance and velocity, and then we started talking about area under a curve, and then we practiced our antiderivatives and our integrals a bit. Now let's head back to distance. This really kind of falls under the category of applications of integrals, which is technically the next chapter, but we will deal with this particular application in this chapter. What we've got here is a velocity curve. So we know the velocity of whatever this thing is at every moment in time. And it's really traditional in these kinds of problems that they talk about a particle moving in a straight line. As I mentioned before, if we don't move in a straight line, we need more variables than we have available to us in Calc 1. So we've got something that's moving according to this rule from time 0 to time 5, so over a 5-second period. And we're looking for two things. We're looking for how far that thing traveled, that's distance, and we're also looking for displacement, which is how far does it end up from where it started. Okay, let's take a look at this curve. I took the liberty of putting in the calculator before we started here. That's 2t minus 4. And you'll see that the value of this function is negative between 0 and 2. This thing is going backwards for the first 2 out of these 5 seconds. So it's going to go backwards some amount of time, and then it's going to go forward for some amount of time, specifically backward for 2 seconds, forward for 3 seconds. So it's going to travel some distance back and some distance forward, which means those distances are going to cancel each other out. So if we want to find out where this thing ends up, second Calc 7, we want to go from 0 to 5. That gives us 5. Now that's how far ahead of where we started we end up. So we're going backwards during this period of time, forward during this period of time. We're going to end up 5 feet ahead of where we started. But how far did we actually travel? To do that, we need to look at where we hit 0 there. So second Calc 7, from 0 to 2. Sorry, I didn't have that on the screen there. From 0 to 2 will give us negative 4. And I apologize, this all stays shaded in. It gives us negative 4. And then if we do second Calc 7 from 2 to 5, we get 9. So what happened here, we've got a curve that looks roughly like this. The area of this little triangle down here is 4. We went 4 feet backwards, and then we went 9 feet forwards. So the total distance we traveled was 13, the 4 plus the 9. The displacement, how far we ended up from where we started, is 5. And how that works calculus-wise is the easy thing to calculate. If we just did the integral of our velocity with respect to t from 0 to 5, that gives us our displacement. That will give us how far we ended up from where we started. If we want to find the actual distance here, then we're going to have to do the integral from where we started to where we hit 0 and change direction. So we'll go from 0 to 2 vt dt and do the absolute value of that, right? That gives us negative 4, but we want to consider that positive if we're talking about distance travel. And then we would add on the integral from 2 to 5, blah, blah, blah. I don't think I need to finish writing that for you. So there's the distinction. Just doing the integral will give us how far you end up from where you started. If you do the integral over the negative direction period and the positive direction period, that's going to give you the total distance traveled. An easy cheat to do that in the calculator is if we want to consider this distance to be positive, we can just go in here and instead of doing 2x minus 4, let's do the absolute value. Okay, so I went to math and then arrowed over, enter for absolute value, and then 2x minus 4. And what that does is it takes everything that would be below the x-axis and sort of folds it up above the x-axis. Now we can do second calc 7 from 0 to 5, and it will automatically consider that backwards part to be forwards, and that will give us our, doesn't do it very well, limitations of the programming, but you should understand that some with numbers as simple as what we put in there, 12.99 whatever probably means 13. Now let's look at a slightly different example here, and I think I copied this incorrectly out of my notes. I did. That's just supposed to be from 0 to 3, and that belongs to our next lecture here. So we have a different velocity, 2t minus t squared, from time equals 0 to time equals 3. So let's put that right in the calculator. 2t minus t squared. You can do these by hand, but I really don't think there's any reason to. The integration is tedious and repetitive, and we don't really need to do it. So we've got our curve here, which is positive for the first 2 seconds and then goes negative. If we want to find our displacement, second calc 7 from 0 to 3, it'll shade that in, and we will get 0. So our displacement's 0. We were going forward for part of the time. I don't know how well that's showing up on the screen. We got a situation like that. We were going forward part of the time and backward part of the time, and those two ended up canceling each other out. So we end up with a displacement of 0. We end up right back where we started. But that doesn't mean we didn't travel any distance. We were going forward and then backward, and we can find that by doing second calc 7 and going from 0 to 2. It's pretty easy to tell. That's got an x-intercept at 2, so that's where we want to go to. And that shows us that we went forward 1.33, so 1 1/3 or 4/3. So our distance traveled was we went 4/3 forward, and then of course to end up back where we started, we must have gone 4/3 backward. So 8/3 of whatever unit we're dealing with was our actual distance traveled. Right? Those are pretty easy with a little practice. My advice is just to do them in the calculator. There's no need to work them out by hand.